Well, hello. Welcome to the class 22. And this is getting near the end of the semester now. We've got just a few more classes left. And today we're going to talk about is Lab 10, which is the last lab you will have. There may be another one that's just for fun that I could post for bonus points. This also has a chance for quite a few bonus points, so this may be the last one. There are some required things in this, so let me go and get to what we're going to talk about today. So last time we talked about UDP and how it differed from TCP. And we had some code for opening or creating the socket, setting it to non-blocking, which could be important for a game because you want to continue doing things and not stop and wait when it's trying to receive or send something on that socket. And then we set up the server address. We sent a message. We use send to instead of send, which you'll notice send to does not block and wait for some confirmation. It just sends it out like a message in a bottle thrown in the ocean, and then it continues on. So this won't block. And then down here, when we try to get a receive from, that will either succeed or fail. If there's data available, it'll get it. If there's not data available to receive, it'll, in this case, hit this exception and put none into both the message and the address. Now, if there is a message, if the message isn't none, then we can process it with a process message function, or we could just stick code in here directly. And on the server side, we do the same thing. There's one extra step in setting up the socket, and that's binding it to the server's address. That's the address that's going to be receiving messages and then responding to them. And then we have the same kind of code here to receive data. And in our code that we posted last lecture, remember we added a loop around this stuff to get all of the messages and process them. We included this process message in that loop. So in other words, we get a message, process it, get a message, process it. We do that until all of them have been processed. And then we send out responses. And we had done code before that kind of embodied this idea for our game server. And the basic idea of the protocol was send input and control events from the client to the server. The server updates the game state to some new game state based upon that information it received from the clients that were ready at the time. And then it sends out a new game state to all of the clients. And since they have their own loop that's receiving that, they'll receive the game state packets. They'll update what they see on the screen. Now, the process then just keeps repeating on both sides. Server receiving all the packets, updating the game state, sending it out to everybody. Get all the packets, update the game state, send it out to everybody. So that's what the server is going to be doing. On the client, it's going to be getting input, sending it to the server, getting any packets that came back from the server, and then which would include the game state, and then rendering that on the screen, and then going back up again. So you have those two different loops that were happening. And we also needed a little bit of code added so the server had the ability for players to join, because it has to know who to send the game state to. In order to keep track of that, when somebody joins, it adds them to a table. In our case, we used a list for that. And then if players exited, we took them out of that list. So we weren't sending game states to players that didn't want them anymore. And the idea there is that we need a way to encode the data. We chose message pack. When we did that last time, it's fast, it's compact, language independent. I like using message pack for game related things because it's compact and fast. If you want something more human readable, I'd suggest using JSON. And if you want something more low level, then struct.pack works great. If you want something that's more geared specifically toward Python objects and can do send on pretty much any Python object that's pickleable, maybe use pickle. But message pack is a pretty good choice, even though it's not built into Python. It's super easy to import message pack, and it works the same way as pickle or JSON. Usually dumps and loads. Really easy to use. Now, so this is what we're going to build. We already built this last time. But here's the client loop, get the user events, send the user event information to the server in a UDP packet. If the data arrives, that should say from the server, receive the game state packet, and then update our local display and render that display, and then repeat that over and over again. On the server side, we're going to receive events, any event that's pending from all the clients. We're then going to, if it's a client joined event, we add an entry to our table. If it's a client exit event, we remove them from the table. If it's another event, then we update the game state based on that event and execute the simulation of the game, and then send to get the new game state. Send that out to all clients in the table. So there were some potential problems there that we had talked about last time as well. And those were events could be lost or received out of order from how they were sent. Game state responses could be lost or received out of order. Different event types have to be sent, maybe even at the same time. Like you might have a mouse click and a key down that happen simultaneously. So why send 2 UDP packets when you could send 1? And maybe it's okay to send 2. Maybe you want to combine those together. And different game state updates have to be sent repeatedly by the server. So the server is going to update, send, update, send, update, send. And the game state could be so large that multiple fragments are needed. For our case, that's not really the case. But we want it to all be quick, so we want to keep the size of that small. One of the motivations we took into consideration and why we're using message pack. Okay. So we pinned down our protocols for our example code to support whatever keys need to be pushed down, detected as pushed down, detected as up, a way to join, a way to exit, and then some keep alive. Now, we didn't add that to our protocol because if we only send something when the key goes down and only send something when the key goes up, what if they're just sitting there watching, waiting for their moment to pounce? We don't want them to be kicked out of the server, but conversely, we don't want the program them to close the program and have the server just constantly sending game state to somebody who's no longer has a program running. And that's one of the things about UDP is since it is kind of datagram based, where you're just making a letter and throwing it into the ocean, again, like a message in a bottle you're tossing in the ocean. You don't want to keep spending the time and effort tossing things into the stream that doesn't go to anybody, that nobody's going to be receiving. So that's what the purpose of keep alive behavior is some kind of message that periodically comes in, even if the game state keyboard has not changed or something like that. Now, there are several ways to do that. We're going to talk about that here a little bit in a second. Now, the other part of this that's worth mentioning is the server to client. It has that player list. It might have a bullet list. It might have an item list. It has all of that stuff it needs to send. And if you look at that version 2 that we created, or 3 that we created last class, I showed you how to create a dictionary, and you just drop items into that dictionary and then use message pack to send the whole thing. But we should probably make sure that we try to keep the size down below the MTU of Ethernet, which is 1,476 bytes. Now, sometimes it's okay to violate that, but we don't really want to necessarily let UDP do that for us, or IP do that for us. It'd be better if we just sent 2 different datagrams. So in other words, if you have a size that exceeds 1,476, it's usually better to say, okay, here's this block of data, and here's this next block of data, because that lets you control if one gets lost, you might have part of the game state update. Now, if it's important that you get both, just let UDP and IP handle that for you. Okay, let's look at the code from last class. And we had some things to consider that we listed here, but let's take a look at the code from last class first, and then we're going to look at the assignment. So let me go ahead and pull that up, so just give me a second here to pull that code up. And I'm going to pull up the UDP client 2 and UDP server 2. I'm going to pull up both of those, so just give me a second here, and then I'll switch over so you can see it. And for some reason, my computer apparently updated, and now I have a completely different user interface in Windows, so it looks a little different here. Okay, so here I have that code open. So let me pull these up side by side, and then I'll switch over to where you can see it. Okay, so let me switch the screen so you can see what's going on here. Okay, so here we have the client on the left. Let me size this so they both fit on the screen here. And then next to that, we have the server. And to give you a reminder, let me hide my pictures, my face, so you can see this a little bit better. Okay, so looking at this, you'll notice we have the client an example. And this is the one that's sending the game state as a dictionary. And notice we have this player client object. On the server, we have this, this player object. And they're a little bit different. Notice the only real difference between these two things is up here. The player object also keeps track of the IP address that that player connected on. It also maintains this the list of what keys are currently down with that player. And then down here, you'll notice that it also has some code where this one renders. This one actually has the code to actually cause that to be moved based on some event that's in the key, or a key that's in the keys down thing there. So this is actually moving it because the server is updating the game state on behalf of that client. And then we still have our render here. Now, normally with a game server, you wouldn't have it rendering on the server. In this case, I added the code to render on the server, so you can kind of follow along and see that when somebody connects, they move around, the server is actually tracking that. And then in our main part of the code, we have these getNet message functions and sendNet message functions for each of these, process net message. And really all that's doing is on the client side to process that net message. It's actually just getting this, whatever packet came in, it's assuming it's game state data, because that's really all that's talking to us right now, is the server is just sending us game state data. And inside of that game state data, we just basically use message pack with the loads and then say, hey, interpret that as this game state dictionary. And one of the things we stuck in that dictionary was the player dictionary list. Now, we could stick other things like a bullet list into there. We could stick in item lists. We could stick in really anything we want into that dictionary and then send it through. And on this end, we can just pull out the parts that we want for where we want to process them. But essentially on this end, what we're doing is we're going through clearing out the player list, and we're creating a new list every time. And then when we render it, we see all those players where they are. So in other words, the player list on the client end is every time we get a new game state, we clear it out, we put everything where it belongs. Now, we could save some effort maybe by leaving them where they are and then only updating them if they're different than our version of them is. So in other words, hey, this person stayed in the same place, don't update it. This person stayed in the same place, don't update it. This one moved, put them in the new location. But what we're doing is we're just saying, throw the entire game state out and rebuild it. And since our game state here only consists of the players and where they are on the screen, we're just recreating it and sending all of that through every time. So there are some techniques to only send things that have changed through from the previous iteration. But that can be a little dangerous because that assumes that we got the previous iteration. So it's a good idea generally with UDP to send the entire game state every time if possible. Now, down in our main loop here, it's relatively simple. All we're doing in our main loop is reading all of the messages that come in with getNet message, processing all the messages. And notice we have that in a while loop. We continue that until we don't have a message. And then down here, we clear the screen, draw all the players in the player list, which was populated by this when we get a message. And then so we're rendering all those on the screen, and then we're updating a display, and that's it. Now, when we exit this loop by hitting escape or hitting the quit X on the screen, we basically send out this quit message. And then up here, what we're doing is anytime there's a key that was pressed, we send a KD event message over the network, a packet that's key down, and then a key up. Now, one of the things about this, let's go ahead and run this and see how this works. But on the server, it's pretty much, or it's very similar. One of the, here, make this a little smaller here, so you can see the scroll bar. Okay, there we go. Now, one of the things on the server side that is different is it's maintaining, if you go down here, it has this active player dictionary, and as somebody joins, it's adding them to that dictionary. It's kind of like the list of things. And then what we're doing is to send the game state every time. We're going through the, for every player that's in that active player dictionary, we're sending them the game state right there. And that, how did we create that? Well, we took the game state dictionary, which includes everything that's in it that was added up here, and we use message pack dumps on this end, and that corresponds to the message pack loads on the other end. And there's the game state string. That's what gets sent to everybody in that UDP packet, and everybody gets it on the other end. All right, now, here's what I want to do is let's just run this to refresh our minds as to how it works. So here's the server. I'll run it first. There's the server code. I'll put that over on this side of the screen at the top. I'll put this Python shell below that, right down here. So that's my server, and notice I named it server at the top there. And then on the client side, let's go and run that one. And there's the client. I'll put that there, and let me move this down here, make this a little smaller. All right, so there we have both the client and the server code running, and now I'm going to click on the client window and I'm going to move that around. So when I press the A key, it moves left, S, D, W. So you'll notice that guy moving around on the screen. You'll notice the server following that, and that's all through packets being sent. Now, that all works great, and if we had another client and entered, they would show up over here as well. If we added another one, they would enter and show up there as well. But you'll notice the only way this is getting shown on the screen is it's not locally being held. This has to have the game state of where, what key is pressed. The state of position where this is entirely tracked on the server, because we're throwing away the player list every time. So when I'm moving this around and I see it moving on this screen, the only way that's happening is a packet's going over here, updating the keys that are pressed, and then this is updating the game state, which only has one player right now, and that's going back out to me over here, and then I'm rendering that on display. So you'll notice those will very closely match each other as long as no packets are lost. And on a local host like this, you're not really going to lose packets, but on a network where it's a multiplayer game across a network that's fairly widely spaced geographically. The server is running in, I don't know, California, and we're playing the game here in Ohio. We might lose more packets or have some of them come in out of order. In this case, though, it's going to work pretty well. It'll work. It'll be very fairly low latency as well. Now, one improvement to that would be for me to, rather than to just throw that out every time, would be for me to track where I think this is going to be the next thing. And then as the message, and then keep rendering that, which would allow me to render this at a high rate. Because right now we have to wait for this to go out and then come back before we see where that is. And in a real game, we would want to say, well, this is how this was moving, so I'm going to predict it's going to be here, and then it's going to be there, it's going to be there. So we would use like the local key information to move that around. But if the server comes in with a message that says it's in a different position than we think it is, than we predicted it was, then we have to go with the server, because it's the thing keeping track of the game state for us. So then we would make an adjustment to make it match what the server said then. And we could do the same thing with the other clients. Now, let's quickly go back to the presentation, and then we're going to look at the actual assignment for what you need to add to this. So let me go back to that presentation here. Give me just a second. Okay, so here's the presentation. We looked at some code. And so now what I want to do is look at the assignment sheet. So let me bring that up. And this is Lab 10, the last one you'll have to do this semester. Okay, so let me move that where you can see that. Okay, so here's what Lab 10 looks like. And what you're going to be doing for Lab 10 in this case is, if we take a look at that code, let me zoom in a little bit here. You're going to be basically using the code that I gave you to start with. So there are some required modifications here. So it says use the client server game code provided in class and modify the code as follows. So the first one here I'm going to help you with. So everybody should get that first one done. But I want you to, what I want you to do there is essentially simulate lost packets or packets being dropped over a long distance network by on the client code, just every once in a while drop one of those packets. And we're going to set, I want you to set that percentage to 5% and 10% and observe the adverse effects that you would have on the operation of that game. And then what I want you to do, so that's the first modification. I'm going to walk you through doing that one. The other ones, however, here, give me a second. I have a call coming in. Okay, sorry for that. But essentially, that's the first modification. I'm going to walk you through that one. The second one, though, is I want you to modify the code so that keep alive messages are sent periodically from the client to the server. And essentially, the way that you do the third thing down here could dramatically impact how you do the keep alive code. So let's talk about both of those for a second here. So the idea there is, if you're not moving, you're not touching a key, the way it's implemented right now, no messages are going to be sent. And the problem with that is the server has no way of knowing the difference between somebody who's just disappeared and somebody who's just sitting there in the game doing nothing. And so what we want to have is some sort of keep alive message that gets sent. And essentially what you want is to say that, hey, if I haven't sent a packet within the last second, then I'm going to send a keep alive message. And the keep alive message, its only purpose is to say that, hey, I'm still here, I'm still here, I'm still here. And the idea is, on the server side, you would build in some code that says, hey, if some certain period has expired and I haven't received any event, and I also haven't, including a keep alive, then I'm going to kick that player out of the game and say they're gone because something bad has happened. They haven't talked to me in a certain amount of time. And so the idea here is relatively simple. And down here, the other thing is I want you to modify the code, enhance the reliability so that when datagrams are dropped, so in other words, if you simulate the dropping of this, it doesn't adversely affect the performance of the game the way it does down here. And I'm going to mention how you can do that. But first I want to show you, let's implement this first one, the code that will throw out a packet from the client to the server. We'll do the 5%, or let's actually do the 10% since it's more likely to get an error. And then we'll see what happens. So let's go ahead and go back to that code for a second. So I'm going to go back to both the client and server code here. Well, first let me exit those two programs. And right now, let me pull up both the client. There's the client code. Here's the server code. Right now, I'm just going to change the client code. So remember, the place that's actually doing the sending here is this send-net message code right there. So that's the thing that's actually sending data to the server. So what I'm going to do is I'm going to make that so that, and notice there's a refactor to use a list of events. And there's a to-do list there. I'm going to take that out for right now. But what we're going to do is I'm going to make a failure percentage, and I'm going to set it equal to 10%. And then what I'm going to do is I'm going to say, make an if statement. I'm going to say if random.randint 1 to 100. So in other words, I'm generating a random number between 1 and 100, and I'm going to say if it ever comes up to be less than or equal to my failure percent, then that means I'm not going to send that message. So in other words, I have a 1 in 10 chance here with that being 10, or a 10 out of 100, which is the same as 1 in 10, or 10% of the time, I'm going to ignore that. So here, I'm just going to do a return from this. And just to make this clear that we're never going to get down here, I'm going to do an else. But really, if you just had the return there, it would work, but I'll do an else there. So in case we wanted to do this or that. So this is the case where I'm going to put a comment here. That's simulating lost packets at that failure percent. So if I want to change this to 10 or 5, I could just put 5 there. Now, that's the only change I made, is every once in a while when I press a key or go to send some packet, we're simulating it being lost. And again, if you work on a network project where you're, and the code that we're looking at here isn't just for games. This is any kind of UDP-based network system. That could be an industrial system that's sending out temperature updates of some machine. It could be a security system that's sending the state of motion detectors and doors and things like that. But if you're implementing some system on top, it could be even a streaming system like Netflix or Amazon Prime, where it's sending out packets that get put together to make the video frames of some sort of codec that's being used to stream audio and video data. The idea here is the same on all of those. But if you're going to work on a system like that and you're going to test that, I would strongly encourage you to implement something like this that you can then test. How does it work under degraded network conditions where packets are getting lost? And this is a good way to do that. And when you're done with this, you could actually still leave this in the code and just set that to like 0, and then it wouldn't lose any of them. It would always work down here. But the idea is, hey, if our number comes up where this is one of the 10% we want to toss, then we simulate that and we can test that on here without having to put it on a large network. And I would suggest that you try your system under various degraded network conditions and make sure that it still works or gracefully under those degraded network conditions. All right, so let's run this again and see what difference we see here. So I'm going to run this one. So here's the server. And notice the server is waiting. And now let's go ahead and run the client. And there's the client. And you notice the client joined. And let me hide my face again since there's no reason to have it in the way there. Okay, anyway, over on the client side, I press the key, it moves around. Now, notice something happened there. I'm gonna press the key like 10 times to move a little bit at a time, moving to the right. So 1, 2, 3, 5, 6, 7, 8. Now I pressed it and it didn't detect it that time. It missed one. 9, 10, 11, 12, 13, 14, 15. There, it missed again. 17, it missed again. Got that one, 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 got that one. Missed again. Missed again. And there it's missed a key up event. So now it's running sideways. And now even if I press A, I'm stuck running sideways because it thinks the D key is being mashed when it's not. And the same thing can happen when I'm moving up and down. Now it's stuck in that bottom corner even though I'm pressing A and W. So only to get back, we press D again, press S again, and now I'm back to moving around. But notice that, and there it is again, it ran off by itself. And that's the kind of thing, I'm stuck at the bottom. That's the kind of thing that will happen if the way we're implementing this right now. So everybody in here should be able to get now those first 5 points by doing that, but I want you to observe what happens and think about why is it sticking there? And the fact is, it just lost one of those events. And if it lost an event, so it got the key down but lost the key up, or lost the key up but got the key down but lost the key up, lost the key up but got the key down. That may have been the same thing. But the idea is, if you can lose those events, it creates a problem because there's no redundancy. We're just sending out packets, and those packets, because we're using UDP, are not reliable. So you might think, well, what would be a better way to do this? And you'll notice it becomes annoying to play this and move it around, because as I'm trying to move around, it keeps running off to the edges and getting stuck, and then I have to press the key in the direction that it was going to recover. So here I'm just going to try to move around in the middle of the screen, and then you'll notice that it will eventually, oh, there it went, and now it's stuck at the bottom because of those lost events. And now it's stuck at the top. And you'll notice that the more degraded we make this, here, let's change that percentage here on the client. Let's make the failure percentage like 50% of the packets get lost, and let's run that. Now this is going to be super annoying. So half of the events are getting lost. So it actually becomes now hard to move and have it make any sense at all. Now I'm stuck at the bottom corner. It's hard to even recover from it now. Oh, now it's stuck up there. I'm going to get it back. I can't get it back. I can't get it down off the top. Oh, okay, now it's not moving. But you'll notice it becomes annoying really quickly. So the question would be, what would be a better way to deal with this? And a better way to deal with this might be to do something like this. Rather than sending out the events like we're sending them now, and let's review what events we're sending. We're sending a key down event, and we're sending a key up event. A better way to do this might be to send an entire list of all the keys that are currently pressed. So in other words, when we get a key down event, we would say, add this key to our local list. If we get a key up event, take the key out of the local list. And then on the receiving end, on the other end, we would have it so that it receives that keys that are currently pressed list, and it reacts to that. And then rather than only sending a message here when a key is pressed, we could send that over and over and over again every time through the loops. In other words, we keep telling the client or the server, here's my keys that are pressed. I'm client 1. Here's the keys that are pressed. Here's the keys that are pressed. Here's the keys that are pressed. And that way, if one packet gets dropped, there'll be another one that follows it shortly thereafter. And if we do something like that, then it doesn't matter if 10% of the packets get dropped, because that would only delay when we see that key event. Now, that delay could matter, so we could associate timestamps with when the key was pressed and when it was released and work that into our simulation. But for your building of this, I would suggest at least sending, rather than a key down and key up event, just send a K event that has the list of keys as they're pressed. So in between here and here would be a list of all the keys that are currently pressed. And if that list is empty, that means no keys are currently pressed that we care about. Now, the cool thing about doing it that way is that would make it so in our main loop, every time we would send the key event. But the other cool thing that can do is that key event, that kind of client key event, can act as our something along the lines of our keep alive. In other words, we can say this is not only just a key event, but it's a keep alive, because we're going to constantly be sending the state to the server. And the server, if those messages stop, what I usually do on the server side, notice here, the way that I'm keeping track of the clients that are connected, you can find that down here with this join event. I take the active player dictionary and I add something in the dictionary at the address. So in other words, I store in the dictionary under that client's address, which includes a port and an IP address, I'm storing who it was that's talking to me. So I have a whole list of those in this dictionary. Well, one of the things you could add to that, rather than just the address being stored in there, well, what's stored in the dictionary is just this player object that we see over here. Well, one of the things that I like to do with that active player dictionary is also store, here's the player objects, is also store an attribute here. It would be something like self dot, oops, that's a caps lock, so self dot last message time stamp. And what I would do is set that to something like time.time. So that's the last message we got. And every time I get a and have an interaction with this player object here, in other words, anytime that I get a message, update this timestamp. And so that way, in other words, reset it to this, but then have part of the code in the main loop that says, hey, if more than, in our case for the lab, if more than 5, if that time grows, the last timestamp was over 5 seconds ago, then delete them out of the thing. So every time I get an event, every time I make a change to this player object, which we are going to be doing every time I get a net message from them. So in other words, in here, I get a message from an address. I return that message and address back. And then what do I do with that? I process that message. Here's where I split it up and figure out what it means. But what I would do is inside of that, where I'm receiving that message, update that timer to say, hey, this active player, you can see us updating the player dictionary down here, active player dictionary. We would just say, anytime I get a message, no matter what type it is, also update the timestamp. And if I were doing this, I would add an update timestamp message here, and then or a method here, and I'd probably also add a check timestamp here that returns a false if the time has expired or they've timed out. And then if that's the case, remove them from the active player dictionary because they're gone now. All right, well, hopefully that makes sense. Let's switch back to the presentation just for a second here. So we looked at the assignment sheet. And actually, let's switch back to the assignment sheet. That's what I probably want to do here. Okay, so those are the required modifications. And this is not a lot of code you have to write here to get these points. We already did this one. Everybody should get those 5 points. The keep alive message, just as long as within 5 seconds of timeout, it kicks them off the server. And over here, modifying the code so that when datagrams are dropped, the game isn't adversely affected, as we saw when I demonstrated that, with things getting thinking a key is stuck. And to do that, send a list of the keys that are currently pressed. That's probably the easiest way to do that, rather than key events. Because if you think about a stateful event like key went down, key went up, that's a lot less reliable than saying, here's the keyboard right now on my client. Same thing with mouse. If you send mouse events, rather than saying mouse move left, mouse move left, mouse move left, it would be better to say mouse is at this X and this Y. Mouse is at this X and this Y. Mouse was clicked on this X and this Y. If you just say moved a little bit to the left, moved a little bit to the left, if those packets get lost, then the two mouse pointers are going to be out of sync with each other. Okay, so in other words, you'll have the server being in a different space than the client is. And that will create problems. Now, the other thing to do here about that is there are other ways to fix this as well, but that's probably the easiest way. So that should get everybody the 20 points there. Notice the nice thing about this is you don't have to know anything about game programming or graphics. None of this has anything to do with the graphics or anything like that. Now, some bonus modifications that I have, you can get up to 30 bonus points, which is pretty significant. Add a turret to each player that can be rotated with the J and the K keys. So in other words, not only will it have like a face like that, add like a little turret, which you can do by drawing a line on there. So in other words, it should look like a, here, let me make a little visual aid for you. The turret should look like, if this is the circle that was the face on the screen, then the turret will look something like this, just the black part of that, and it can rotate around to different angles. Like that. Now, to do that, that means you're also going to have to add a turret angle to the player object. That works, think of that just like the X or the Y. So you'd have self.x, self.y, self.turret angle, and you'd add that to both the server and the client side. And then since you're just sticking that list in the dictionary already, that would automatically get sent, and then you just have to render that on the client side so that you can see the turret angle. So that's going to allow you to do that. Now, the next thing, so that's worth 5 points. And this one is actually relatively easy. It takes like just a few lines of code to add that. Now, bonus 2 says to give each player a health percentage attribute and a score, and display those. You can display those along the bottom of the screen. This will allow for up to 4 players. You can have like player 1, like let's say here, player 2, player 3, player 4, and it would just have their health. And then that's similar to this up here, but even easier in some ways. You'll just have to figure out how to do fonts in Pygame. You can Google Pygame and font if you don't know how, and find some examples of that. But the idea there is you're going to just add a health and a score attribute and show those up. And now the next thing for bonus 3 is to make the bullet or the turret fire a bullet when the space key is pressed. So if the space key is pressed down, add a bullet to the bullet list. And when a player is hit by a bullet, have them lose health. When a player's health gets to 0, they should be killed and respawn with 100% health. Add the networking implementation to support that. So you're going to have to, what I would do is think about how we added that, have the player dictionary as part of the game state dictionary. Just have a bullet list there as well. And then in the main code of the loop, say if the bullet ever hits the player, if any bullet ever hits any player, then they lose some health. If their health gets to 0, then they pick a new X and Y position. And then here for bonus 4, you're going to add local particle effects like an explosion with things like blowing out when the player dies before they respawn. The cool thing about that is you don't need to send all of the particles from the client or from the server to the client as part of the game state. That can only happen on the client side. So in other words, whenever you die, you just make a little burst of particles. The server never needs to render that. The server never needs to know about that. So this one doesn't even really need much in the way of network implementation. That can all be on the client side. So even though it says to add the networking implementation to support that, you don't really need it because it's just a visual effect. And that shows that on games, the reason I added this as a bonus option was that in games that allows you to have certain visual effects that the server doesn't need to know about. Like when you're running and there's dust clouds, the server doesn't care about that. That's just a visual thing for the player to see. The only thing the player cares about is where are the players, what things can cause something about the game state to change. It doesn't need to track all the visual things and the everything that's happening and keep track of that. Now the last one here is to add local prediction to the simulation to make the game appear smoother on the client machines. In other words, you want the game to keep track of each player, where they are on the screen, the direction they're moving, and then if it doesn't get an update packet from the previous frame, consider they're moving in a straight line and just put them there as if they were moving. If it did get an update for that player, put them in the place that the server said they were. And that can allow then the client to run at a much higher frame rate and look a lot smoother. And so when there's network congestion, rather than having things look chunky and kind of popping around, they'll still move smoothly. But then when a packet finally does come in, they will pop into the place where they're supposed to be. And you may have seen something like that in games that you've played online, where there's a player running and then suddenly they pop and they look like they're somewhere else. Now, a well-written network game will make that fairly seamless. In other words, if the local simulation doesn't match the server simulation exactly, rather than just popping it there, it'll slowly over the next few frames make them so they match up so it doesn't look discontinuous. And that's, I've written code like that before, and that can be done pretty simply with just a form of interpolation between the server said I was somewhere different. The server said this object was somewhere different than my simulation showed it was, so I'm going to move towards it fairly rapidly. And there's a really easy way to do an interpolation over the next few frames to make those things match. In other words, if you move a percentage toward it, like 50% toward it on the first frame, and the next frame 50% toward it again, then on the client machine it'll look pretty smooth rather than just popping, and it'll be less noticeable to the user. All right, now what I want you to do, if you do these bonus things at the top of your program when you submit it, tell me which bonus you did, and then I want you to add comments in the code at the locations where you implemented each of these things. So in other words, if you added something for bonus 1, for the turret, then in the class where you added the turret angle, put a little comment there that says bonus 1. And in the code, network code, add a little comment that says bonus 1. So that way I can tell where you added that stuff for each of those items. And then submit that all as one entire zip file. So you don't need to include a separate implementation for each of those. You can turn in just one solution for the required stuff, plus the bonus modifications, but just put a comment at the top. If you don't have that comment at the top, it tells me which ones you did. I'm going to assume you didn't do any of them, and I'm only going to look at the required stuff up here. So to get your points, make sure to add these. And these first two are actually pretty easy. And actually B3, using that approach that we did in class, you just need to send a bullet list. And since we're not keeping track of who killed who in this, then it doesn't really matter. You'll notice that we did have a score here that we added. I don't really have anywhere that that's being updated right now. But if you just say player 1 health score, whatever, health comma score, however you want to output that, then feel free to do that. But that's really the last lab we're going to do this semester. I really wish we had another couple weeks. And really for this UDP kind of game server, for those of you in the gaming degree, I really wish we had a full semester, or at least something like a special topics class where we could spend more time on this, because there's a lot of really cool stuff you can do for keeping track of that game state and having a very lean data stream to have really high performance multiplayer network games. And unfortunately, we're just not going to have time to cover that this semester, and the CET students probably don't care about going too in depth for this. The nice thing about what we're doing here with this UDP code is these techniques that we talked about here will work for not just a game server, but for any real-time client-server architecture that's using UDP. So an industrial network, a security system, I don't know, like a fire reporting system, some sort of machine system that monitors the state of different parts of a machine in a remote way. So Internet of Things kind of stuff. So all of that stuff. I might post one final lecture just for fun next week. But realistically, we've only got a couple classes left, and I want to give you time to study and have the study guide posted. So I'm going to post the study guide next week and give you next week to work on the labs and ask questions. Okay, so that's it for today. Let me quickly go back to the presentation. So we looked at the assignment sheet, and that's it. Work on those labs. Stay safe. If you are struggling with any of those, let me know. I'll be happy to help. But hopefully you learned a good bit this semester, stuff that you can use. Those concepts that we talked about throughout the semester are really useful and powerful things. For example, a lot of the stuff I've done in my career as an engineer and as a programmer has used those concepts, everything from CRC to RS-232, SPI, I2C, network programming, the kind of things that we did in here. There are some other topics I wish we had time for, so I'd encourage you to continue your study of those things. Like WebSockets are a good technology to look at. It allows code that runs in a browser to use sockets to talk over the network to other code. And then I've also, there are tons of other things in networking that wind up having uses in other areas. For example, the CRC calculations we did, there are uses for those in data structures, for putting, computing a hash value for something that you're storing in a binary tree or a heap or something along those lines. So there are tons of uses for the technology beyond what we've talked about in class. So I'd encourage you to keep those things in mind. All right, so that's it for today. We came in, I wanted to be in at 45 minutes. We're right about 50, so went a little bit over. But work on the labs, stay safe, send me an email, shoot me a text message if you're having trouble, and we'll set up a Zoom, or I'll answer as best I can. And that's it. And next week, look for that study guide and maybe a little bonus lecture that will have some stuff that won't be on the final. But I think there's some other fun things that I'd like to just show you. So we might have one more lecture. That's it.